In Chapter 10, we'll start to look at how we reconstruct past climates. Where do we get our information from? Part 1 will look at evidence from the ice, including ice sheets, glaciers, glacial striations, things like that, as well as ice cores in Antarctica and Greenland. We'll also look at ancient sediments and also sea level changes. Proxy data is used to infer past climates. Examples of proxy data would be pollens over here, dendrochronology, the study of tree rings, any kind of ocean sediments, ancient soils, ice cores shown in the lower right here. Also looking at geological strata, as this person's indicating here, corals, and also written records. Now, glaciers are a good example. Obviously, glaciers form when it's cold. Glaciers are slow-moving rivers of ice, mountain glaciers specifically, or sometimes they're large mounds of ice, like the continental glaciers which exist over Greenland and Antarctica today. Here we're looking at Commonwealth Bay in Antarctica. Here's a picture from Greenland showing a moraine, so geological evidence from glaciation. A moraine, as shown in the last picture there, a geological feature caused by glaciers. Glaciers essentially carve out large, deep, U-shaped valleys that are a signature that a glacier caused them. Material pushed around by the movement of glaciers. Glaciers can push rocks ahead of them and underneath, and in so doing they can grind up the rocks, they can push the rocks into certain formations as evidence that a glacier was there in the past. Material on top of glaciers can eventually fall to the base. Imagine, for example, some rocks falling down the cliffs here onto this glacier that over long periods of time are moved down by the ice, and perhaps when that glacier melts, that rock is put into a place where there's no other rocks like it. So that's what's called a glacial erratic. So these erratics can form not only in mountain glaciers that carry rocks from the top of the mountain down towards the bottom where they don't match the local geology. It can actually happen on the edges of continental glaciers. So in the deep past, we have evidence in the ocean sediments of rocks that definitely came from a land source. And so the question is, how did they get there? And the answer is that these drop stones, they call them, you must have had a continental glacier somewhere where it calves off ice that contains some rocks from the local geology in the continent, and then that ice raft floated around for some time before it melted, depositing its rock into the oceanic sediments. So this gives us evidence that there was glaciers at those times to the extent of the continental coastlines. Glaciers at the last glacial maximum 20,000 years ago. This is the Laurentide ice sheet, which is about 3 to 4 kilometers thick of ice, encompassing all the way down from Minnesota, Wisconsin, its furthest extent at this period of time. So essentially during the Pleistocene, the last 2 million years, we've had this oscillation of ice caps growing down towards the mid-latitudes. That would be called a glacial period during that time, and then ice caps retreating back towards, say, the extent they are today, like Greenland and just Antarctica, so a minimum extent of ice called an interglacial. There's a lot of geological evidence for these regular glaciations that happened over time during the Pleistocene in the form of moraines, glacial striations, which are scratching of the rocks from glaciers and the rocks that they carry, and other glacial evidence as well. So for mountains, it's pretty simple. The glaciers travel downhill relatively slowly. The reason why that happens is because as ice gets compacted at the very bottom, that extreme weight actually caused what's called plastic deformation. So glaciers actually have some movement at the base when the ice is under extreme pressure, and this is why they move very slowly downhill. In the case of a continental glacier, you don't have that downhill effect. So what causes ice to move towards the edges of the continents and calve off as icebergs into the ocean? Well, the large ice sheets tend to be dome-shaped, as shown here. Obviously an extreme example. Let's just imagine this is Antarctica. Just like pushing down on a pile of jello, the weight of the ice literally squeezes out the ice on the sides in what's called basal stress. So just stress formed along horizontally trying to push outward. So effectively, gravity's force is pushing straight down, but at the same time, this translates into higher gravitational effects where the ice is highest, less where the ice is thinner, and so there's a net movement towards the sides in what's called basal stress. The ice eventually will break off at the continental margins in what's called a calving event. Each year's ice layer becomes thinner and thinner over time due to the compression of the ice over time, as shown by the green lines. So one thing that's interesting about this, if you're going to take an ice core to see an example of how the snow evolved over time, and actually we can use in those ice cores, we can look at the bubbles for CO2, other greenhouse gases, as well as understand what's in the water itself that we'll get into. You really want to take your ice core in the center of the dome. And this is exactly what we do in Antarctica, and this is why many of the cores in Antarctica are called Dome A, Dome C, etc. Because if you take your ice core off the middle of the dome, you're influenced by this basal stress and this horizontal movement. So your understanding of which layer maps to what time over history becomes distorted if you take your ice core in the sides. That's why we take them in the middle. Here's some example of glacial cycles as seen in the Vostok ice core. This is a core from Antarctica, which runs about 420,000 years back. Starting from present now, we're going backwards in time to the right here. The first thing I want to say is that the Pleistocene, when we do see these fluctuations in temperature over time, extended from about 12,000 years ago all the way to 2 million years ago. This part here in the last 12,000 years is called the Holocene, which is a time where the climate has been quite a bit more stable than it was back in the Pleistocene. So what's seen here, the purples in the upper part of the graph are CO2 concentrations, as found by grinding each layer of ice in the ice core and seeing what kind of gas comes out of the bubbles. So they measure that and see oscillations every 100,000 years. They do the same with methane every 100,000 years roughly. Here's inferred temperature, and I'll get into in the next few slides of how do we infer temperature from the water content. But the keys here are that they are in tune with the eccentricity orbital cycles. So during the Pleistocene, we do see this periodic oscillation of temperature, CO2, and methane together. And so one thing you cannot say here is that it's definitely CO2 rising and falling and that's pushing the temperature. As we'll see later on in the course, there are ways that temperature can change the amount of CO2 in the atmosphere too. So we can certainly say for now they're well correlated, but we'll have to look further for more evidence of causation. All these arrows are pointing at glacial periods where the temperature is at its lowest every 100,000 years. And the last one again was roughly 20,000 years ago. So what is inferred temperature? How do we infer temperature in these cores? First we look at oxygen isotopes. Normal oxygen has 8 neutrons and 8 protons and an atomic weight of 16. A small fraction of oxygen has 2 extra neutrons and its atomic weight is 18, so we call it O18. Hydrogen typically has an atomic weight of 1. So in water, we can have normal H2O or heavy water, H2O18. There are other species too. Here's normal water, 18 grams per mole with a 16 plus 2 ones. Here's H2O18 with 18 plus 2 ones, making it 20 grams per mole, a little heavier. And then here's HDO, where one of the hydrogens actually weighs 2 grams per mole because it has an extra neutron. And this molecule we call deuterium, which is also measured in the ice cores and used to infer temperature. So how this works in the water cycle, you say you have some ocean water with some certain ratio of heavy to light isotopes, H2O to H2O18. When evaporation occurs, it's easier to evaporate the lighter isotopes than it is the heavier isotopes. So you get more of those lighter isotopes evaporating. When it condenses, it goes the other direction. It's easier to condense out the heavy isotopes than the lighter isotopes. So therefore, in the water cycle, you tend to dump out or remove by precipitation the heavier isotopes anytime you have precipitation. So when the pole is extremely cold and there's a strong equator to pole temperature gradient, you'll have more condensation from, say, the subtropics where most of the world's water is evaporated to the pole. If you have more condensation from A to B, you're going to lose more heavy isotopes on the way to the polar ice sheet. What is left then on a cold polar year are lighter isotopes to fall into the snow on Antarctica and eventually make those layers in the ice cores. I want to point out that the book has this wrong. On cold polar years, you have lighter isotopes falling into the Antarctic ice sheet. On a relatively warm year in the poles, where the equator to pole temperature gradient is reduced, not as much condensation from A to B, doesn't remove as much heavy isotopes. So on a warm polar year, you have a relatively higher amount of heavy isotopes, and on a cold polar year, less heavy isotopes in the snowpack. So during anomalously cold polar periods, the snow that falls in Antarctica is relatively depleted in those heavy isotopes. You can either consider depleted in HDO, which is a heavy isotope, or H2O18, which is another heavy isotope, in comparison to just simple H2O. What does this imply about the isotopic composition of precipitation that falls into the ocean along the air mass's journey from the tropics to the poles. In other words, there must be a balance here. A greater proportion of heavy isotopes must have precipitated into the ocean en route compared to normal years. So in a cold polar year, if you're forcing more condensation, you're dumping the heavy isotopes into the ocean, leaving less for the polar snowpack. Why I point this out is because we have marine isotope records that go back way further in time than polar ice cores do. Here's the Vostok ice period record 400,000 years back. Here's a marine sediment record that goes back more than 3 million years. The oldest ice core we have, the deepest ice core that goes back the most in time, is roughly 800,000 years in what's called Dome C. So this extends our knowledge of climate by going way further back in time, drilling into the ocean cores and looking what's in there. So in colder times means less than normal amounts of heavy isotopes piled up in the ice sheets. Where's the heavy isotopes? They must have fallen in the ocean. So you could look at drilling cores and corals. They're not going to go back nearly as far. This particular record, as I mentioned, is looking at the deep sea record of seawater as analyzed by looking at the ocean sediments there and looking at the biology, because in the isotope world, you are what you eat. So anytime those animals are around, they're taking in the isotopic concentration in the oceans at the time. When they die, that signal is sequestered with them. They pile up over time, in this case more than 3 million years, and we can dig them up and look at the isotopes within them and infer temperature from there. So what a delta value is, it's comparing the amount of O18 to O16, so the ratio of the two, to some standard, and then expression the deviation. So what they're showing is when the delta O18 values are low, that means you have less O18 than is typical, and that would make sense when you're in a warm period. Because the Antarctica is relatively warm, you're not pushing as much heavy isotopes into the ocean as typical, and so you're going to have less falling into the ocean, low delta values. When the delta values are relatively high, you're pushing more heavy water into the ocean, and that corresponds with glacial periods when Antarctica is very cold. One thing I'll point out in this record is here's those oscillations between glacial and interglacial during the Pleistocene, which this goes all the way through the Pleistocene here. So for the last 700,000 years, the periodicity has been about 100,000 years. Before that, it was still in tune with the Milankovitch cycles, but more in tune with the tilt or the obliquity. So now you have a good idea of how we infer temperature, both in the ice cores and in marine sediments. We're looking at isotopic concentrations over time as a result of precipitation history, which is a strong function of the pole to equator temperature gradient. Because of course, the colder the pole is, the more it forces saturation and precipitation en route. Ancient sediments, salt deposits. If evaporation exceeds precipitation for a long time, that's going to remove a lot of fresh water from an oceanic basin. As that happens, the salt concentrations rise. If they rise enough, the salts will concentrate and actually crystallize and precipitate from the local waters and form sedimentary layers, which of course a climatologist can dig up later and infer the evaporation versus precipitation rates at that time. There's also wind deposited materials. Sand dunes, for example, are used to assess prevailing winds in the past. Also loss, which is dust formed by extreme glacial abrasion. Those deposits can be found around and inferring the primary wind directions at the time that was happening. Ocean sediments, these offer long timescale views at climate using accumulation rates, how much sediment's forming over time. That can be a function of storms, a whole bunch of other processes, and also, like I pointed out, isotopic analysis of fossils and planktons, because in the isotope world, you are what you eat, and you're going to sequester that signal. Now we have kind of an interesting deposit zone called the Great Sand Dunes National Park in the San Luis Valley in South Colorado. Now what happened here was there's a huge closed basin lake in the San Luis Valley called Alamosa Lake that created sands over time by all the friction happening between the water and the surface, and then by climate change, the lake dried up, leaving the sands behind. What happens these days in the San Luis Valley is the prevailing winds are typically southwest to northeast, so they tend to blow a lot of the valley's sands up against the mountains here, forming the Great Sand Dunes National Park. These southwest winds are particularly prevalent here because there's a pass called Medano Pass which offers a gateway for winds to flow through. Otherwise, the Sangre de Cristo Mountains here are quite tall. At the same time, as the mountains cool off every night, you get what's called drainage winds, because that high density cold air will flow downhill, and that tends to push the sands back down a little bit. You can also get storm winds from the mountains doing the same thing. So there's a battle between the prevailing southwest winds pushing it up against the mountains and trying to push it over, and drainage and storm winds trying to push it back down, so there's some kind of balance there. At the same time, the rivers play a big part here too, especially in the spring, where Medano Creek, this river coming down along the side here, actually eats away at the sand dune and recycles the sand that was deposited by the southwest winds and pushes it back to a place where it can be blown up again. A similar type creek does the same thing on the north side and pushes sand around this time. So there's a whole recycling of sand, and that's why it stays positioned, but it's very dynamic in that there's all kinds of processes moving it. The next picture I'm going to show you is from what's called the sand pit, kind of on the southeast side over here, in a place where Medano Creek flows pretty well in April and May specifically. So here it is, the sand pit on the southeast side. You can see clearly that the creek, Medano Creek, is digging into this sand. You can see the sand in the water, and it's digging it out, bringing it around to the southwest side of the dunes so it can be recycled. This is really a seasonal creek, or at least it gets extremely low during the height of the summer. So this is the most active process during April, May, into June if it's a wetter year. Sea level changes can be caused by two major things. Changes in the volume of the ocean basins. This is a slow process. As we've mentioned, plate tectonics and simply shift the plates around, changing volumes. You could also imagine sedimentation rates. As you add sediment to the ocean bottoms, that's going to decrease the volume as you're increasing the height of the seafloor. Volcanism can do the same thing from below. Hawaii is a good example where you get volcanoes coming up from the bottom. That's obviously going to take up space, decreasing the volume overall. A faster way to change the volume of the water is land ice melting and freezing. Anytime you melt land ice that's not buoyed up by the water itself, if its weight goes into the water, it's definitely going to raise sea levels. The Antarctic sea level rise equivalent is about 70 meters total if you melted all of Antarctica, including East and West Antarctica. That's not likely to happen anytime in the future. Greenland sea level rise equivalent would be about 7 meters total if you melted it all. And that's also not going to happen in the near future. However, both Greenland and West Antarctica, the lower elevation part of Antarctica, are actively melting right now, contributing to sea level. I'm just not suggesting that the entire ice pack is going to melt just yet. Thermal expansion's another factor here. Anytime water gets warm, it expands and it gets less dense, so it takes up more volume. So warmer waters will definitely increase sea levels. If Greenland's ice sheet were to melt quickly and entirely, again, not likely to happen in the near future, who would see the largest increase in sea level? Would it be places near Greenland? Would it be places far from Greenland? Or would everybody's rise be about the same? The answer is actually places far from Greenland, and let me show you a quick video to show why.
Near a melting ice sheet, two opposing effects influence local sea level. A weakening gravitational attraction lowers the sea near the ice sheet, while at the same time, water flowing into the ocean raises it. To take a concrete example, imagine that the Greenland ice sheet suddenly collapsed into the sea. Globally, the meltwater would raise sea level by an average of about 22 feet. But relatively nearby, in places like Scotland, Norway, and Newfoundland, the disappearance of the ice sheet's gravitational tug on ocean water would cause sea level to drop.
So somewhat counterintuitive, but it is true that locally the waters would go down because of the reduced gravitational attraction. Of course, we should be most concerned with the global sea level rise if that actually happened. Key points from here: evidence from ice. Glaciers leave evidence, thus we know when it was cold. We infer temperature in ice cores by water's isotopic fractionations that happen during transport. Ancient sediments can be used to infer evaporation minus precipitation values, or the balance there, from salt deposits. Anywhere we see salt deposits, we know it's extremely high evaporation rates that superseded precipitation rates for a long time. We can infer past winds from dunes and also lost deposits. Sea level changes. We can infer past temperatures by sea level rise and falls or fluctuations in sea levels. Of course, we know when it's cold, a lot of that water will be tied up in glacial ice packs, and therefore sea levels would be expected to drop. And that's exactly what happens whenever we're in a glacial period. Sea levels will drop a lot. If you're going into the past, you're looking at sea level drops of 300 or 400 feet at the times when glaciers are at their strongest.